Hello, this is Matt, ham radio, call sign KK4NDE. Going to try and talk about some methods I use for testing power supplies and cables. I've been meaning to update my website regarding this, but just haven't gotten around to adding the latest and greatest details. So, before I get going on what I really wanted to, which was some USBC power supplies and cables, finally got a method for testing those that I think is reasonable, but I thought I'd also give a quick overview of the other methods that I've used for testing various things. So this piece of equipment is a 2 strips of wood with holes drilled through for, they're just car brake lights. They're all wired in parallel with a switch on each, so that gives me 10 of them, 2 amps up to 20 amps in increments of 2, and that lets me do a test on a higher current power supply to make sure it's up to spec. So let me give a brief demonstration of that. To power this, I've got a bench power supply that I use for my radio gear, 13.8 volts up to 30 amps. It is a Samlex 1235M, and then I just have an adapter from my high current to my standard Anderson power pole connectors here. I'll plug into a feed I have that runs to the front of the bench. So and for these higher current, higher voltage tests, there's a little, bear with me with the camera focusing. This is sort of a new thing I'm trying here today. Got this little load tester. They're not too expensive on Amazon or whatever, but it will give you some information. Come on, focus please. I'm not sure how I feel about autofocus, but it gives some readouts. So now I'll try and plug this guy in, and it may be a little bit bright, but here we go. So I'll turn on. That's 2.5 amp, oh, 2.1 amps, there we go. The filaments change slightly as they warm up, but this thing, you can turn on a bunch of, any number of these. Let me get this out of frame, because it's a little bit bright, I have to agree. See if I can zoom back in on this for you to see what it reads. That autofocus is really not happy. I may have to do something about that. There you go. So you can sort of see the readings, 20.7 amps. And if I turn off a couple of these, drops down 16 amps. Turn off a couple more. Oops, went out of frame there. On down to 0 as I turn them all off. So that works well for higher current loads, but that wasn't really what I started this to talk about. That's just a high-level thing. Since this one's built with car tail light bulbs, they'll run nicely at 12 volts, and you can let them go for a fair period of time as long as nothing's sitting on them, because obviously they get rather hot being incandescent bulbs. They have to be incandescent because the whole point of it is to dissipate the power and get a reading on a amount of load. So let me swap this back here. The other power supply thing I'm going to be using for some of this is a box that I built to give me 3 10 amp 12 volt power sockets to simulate using a car power at the bench here. So that gives me up to 30 amps, 3 sockets, 10 amps a piece. It's fused separately for testing different things. So let me go over what's out here briefly. So for testers for USB, first thing that I have here, let me try and zoom in a little, is this USB tester. And what this will give you is a small display. Let me try and power this guy up. A small display, and it gives you a readout in volts and amps and watts. So you can see it's 5 volts, 0 amps, and 0 watts. And then also a load test, which is just a simple static load test, 1 amp or 2 amp. It's got resistors, so I can plug that into the tester. And now you can see it's reading about an amp, about 2 amps. 4.8 volts is about the lowest that I like to see things when I test, because if it's supposed to be 5 volts, plus or minus a reasonable percent, I've just decided that 4.8 is what I like to have. And this meter is the same deal. This one just happens to be a slightly different form factor. I like it better because it's got a little pigtail on it. Also, the numbers are slightly larger, a little bit more readable from a distance. So this is my preferred one, but you have to click through the different modes. It doesn't just give you everything clean on a OLED like this one does. But that's okay, because most of the time what you want is the volts and amps, and that's good enough for these tests. So these little adapters I'm playing with, the first one I made, but what it does is it gives you either USB mini or USB micro. I've got another one over here. I got a USB C to C coupler and C to A cable. So just that way you can plug the meter into a normal USB-A female port, so you can measure the device side of a cable and see what the device would be seeing for power. So that way you can measure the loss in a cable from the power supply end to the other end. The other meter I have here is a USB-C power meter, and if I plug it in, you can see what it does. It gives you the voltage, amperage, and milliamp hours. That's all this one does. But it's enough to get a good idea of what things are looking like, what power profile something's running at. It seems to support both, well, all of these seem to support Qualcomm Quick Charge. I only finally now have one device that supports it. I haven't devised a good way to test it. This one also supports USB-C power delivery profiles. That's what a lot more things seem to use. So I'll get into that a little more later. And then for test loads, initially I started with this 50 watt 10 ohm rheostat, and I just made some marks where things seem to be. Obviously you don't want to go all the way up and have a short circuit. That's bad, but you know, you can go up here to a little bit of resistance to 2.5 amps, or all the way down to the full scale around 480 milliamps. I calibrated these lines by using a multimeter and measuring the current and voltage. More recently, to test higher power things, I built this, which is just two 100 watt 4 ohm resistors bolted to a very large heat sink with thermal compound so it can dissipate larger amounts of heat. And then to fine tune it, I use a 100 watt 5 ohm rheostat, and it's the same basic idea. And by using combinations of these two in parallel or series here, and then putting this in series with those in parallel or series with, I can get a number of different useful amounts of resistance, useful amounts of load on a bunch of different voltage profiles, anywhere from 5 volts up to 20 volts, a couple of amps. So that works out pretty well. And then to connect these up, I have a power pole to some jumper leads, USB-A to power pole. It's probably a little bit dangerous because if you absent-mindedly plug this into 12 volts, plug that into a computer, it's probably going to do something bad. Then just some 18 gauge nice fat jumper cables. Go from one thing to another and hook up whatever I need to hook up. For a power supply here for USB-A, I've got an Anker. I think it's a 65 watt is, I don't want to say the wrong thing here. It's a model A2053 power port plus 5 USB-C. It supports power delivery USB-C as well as 4 normal USB-A ports. It gives me a pretty good power output. I've got some nice short cables on here. And then one of the things I'm going to be doing testing on before I review it is this USB-C. It's a USB-C power delivery and Qualcomm quick charge power adapter for your car. Now that I have a new phone that supports that, I am more interested in having a good unit. Then just some regular USB-C to C cables for hooking things up to test. I happen to already do some tests with these. I know they seem to be reasonably good. A USB-A to C cable. And the other cool little gadget that I'm going to be using, two gadgets actually, is a couple of these boards I got off of Tindy. One of them is a USB PD Buddy Sync. The other is a Y cable for the PD Buddy Sync. Let me zoom in on these a little bit so hopefully you can see those. And what this does is this can speak to a USB-C power delivery supply and put it in different modes and give you plus and minus volts out at reasonable current. This gives you a Y cable so you can connect a computer to the serial port on this for configuration, while this is also plugged into a power supply. So you can do things like query what the available profiles are to see what a power supply really supports. Regardless of its printed specifications, you can query and see what the chip inside of the power supply supports. So I have one of those in a 3D printed case here as well, with a couple of leads coming off of it for my ease of use. But this runs for about $30. I thought it was a reasonable price. I was wanting to make something like that, and then I found this fella on here, Clayton G Hobbs, that seems to sell it. And since it is smaller than what I think I could make myself, and it does exactly what I want, I think it's worth every bit of the $30. I've gotten several of them. I've been extremely happy with them. In fact, here's one of them in a little 3D printed case, and it is set up so that I can use it for, come on camera, so I can use it for power poles, so I can get a small amount of power out, charge a handheld radio or something from a USB-C power bank. So that's sort of a handy thing to have around. It's, portable 12-volt power supply, 12 volt or 15 volt, depending on which profiles the supply supports that you plug it into. So, now that I've done a, now that I've done an overview of some of this equipment, let me try and go through a couple of the high-level tests. So, let me start this by bringing in the car power surrogate unit, since what I'm interested in testing at this point is a car power supply. And we will plug this guy into the top here. Lights up. And I'm just going to start by plugging in this meter into the normal USB port, and let's see what we get for voltage. It's 5.24 volts at 0 amps. That makes sense. Seems reasonable. Since I'm expecting this to go up to somewhere in the neighborhood of 2 to 3 amps, let me get these out of the way here before I lose them. I'm going to just go ahead and use this guy because it's fairly simple and it's fairly effective. So what I'm going to do here is plug together my power pole jumper leads onto my USB-A port adapter. Plug it into the meter. If you're using, you want to use the output one on this little X-Dragon meter if you're using the quick charge or power delivery or whatever type device, because the device has to speak over the data pins. For this, it doesn't really matter. Output 2 is charging only. Output 1, the data pins are connected through. So now I will connect up the plus and the minus to this rheostat here, and we have current flowing. So let me turn off the autofocus because that's probably going to drive everybody on video nuts, and try and get this in slightly tighter so you can see what we are trying to look at here. So as I turn this knob up, you'll see the numbers go up. If I hit 2.5 amps, I'm going to be very satisfied as long as the voltage doesn't creep down too much. There's 2.8 amps, 5.2 volts. I think that's a reasonably good power supply. It's not falling off. Some of these fall off very badly. This one seems to be holding. I could do a longer test and let it sit here and run for 15 minutes or something, but I'll do that off video because that's a little bit boring for you all to watch. Briefly, I do have a cable here so you can see what it looks like for a faulty thing. This cable happens to be faulty. It looks like a nice high quality cable. It feels good. It's got nice strain relief. Nothing's pulling out. But let's see how good it really is. So I'll plug it into here. Actually, no. I want to measure it at the far end. So I'll plug the cable into the charger. I'll plug the device end into this mini micro adapter here. And then I will connect it up to the power supply. Okay, we got 5 volts at 0 amps. That's a great start. Let's connect this up. See how we look. Ooh, at only 300 milliamps, it's pulled it down to 3.6 volts. Let's see if we can go up a little higher in the current. Uh-oh. It dropped so much that the meter doesn't even run. That probably explains why this particular cable wasn't working too good to charge a phone. If I wanted to, I could get a much higher resistance rheostat and find out exactly what it is, but suffice to say, it's not being very useful at all. Okay, so what does a better cable look like? Let me grab somewhere here, I'm sure I have a cable. I had a cable. I'll just pull one of these off of this charger. Plug it into here, plug it into here, and we'll take a look and see what a good cable looks like. This is one that I know will pass with flying colors. So, alrighty. Up over 5 volts at near an amp. I'll keep going up. I happen to know that most of my phones used to charge around 1.8 amps. I'm up here at 2.4 and it's still pushing 5 volts. So, you know, that seems like a pretty good cable. We're only losing maybe 1/4 of a volt at 2 amps. That's the kind of a cable you want to use to charge your phone, because all the power is going to end up going into your device, not being burnt up as heat somewhere along the cable. And that'll work far better to anything else. Now that we've looked at that, we probably want to look at the USB-C port on this, because we looked at the USB-A port. So I'll do an initial test with this adapter. It's just a USB-A to C adapter. And we'll basically do the same test we just did to test the 5-volt portion of that, and then we'll put it on a computer and look at a little bit more elaborate output. So here we go. 5.2, 0.47, that seems very good. I expect this to go up to 3 amps, no problem. There we go, 3.1 amps, 4.9 volts, no problem. Did it easily. USB-C should have no problem pushing that kind of power out, and it has no problem with that. So, let's move on to an actual USB test load. In order to do that, I'll connect up this USBC meter, which I don't know if you'll actually be able to read, but we'll give it a shot, see if you can see it on here. And in order for this to boot up, it needs to have a signal that there's a device because of how USB-C works. So this is where it's going to come into play to get this little board here. And what we do with this is hold in the configuration button on here. Actually, I'm going to use the one that has jumper wires off of it for my convenience. So I left a hole in this case so I can poke my pin in and hold in that configuration button. Snap the Y in so that we can do that. Plug this known working, I happen to know it's working because we did tests on it already. The way you test if the cable's good, you measure if the power supply is good at this end of the cable. Then you put it at the far end of the cable and you test whether or not... this isn't... I didn't have my finger on the button. There we go, I felt it depress this time. And it's blinking to indicate it's in configuration mode. So that means I can talk to a computer. So this will let me do the test. The way you'd find out if the power supply is good, you do this with the meter at the power supply end, see what your readings are, and then we repeat the tests with the meter at the device end and see what the readings are. If the cable's good, they shouldn't be too far off from what was at the power supply end. That way you can subtract, find the difference between the power supply and the device. That's what you're losing in your cable. So, in order to do this, I will plug this computer cable into the UFP port, which is the computer diagnostic port side of the, as I drop the cables and hopefully don't short them. That is the computer side of the device. And after a moment here, I will try and bring the computer over here. Let me try and make a little room. Bear with me a moment. So, if I bring the computer over here, you can see now we have ACM0, which is a serial port device, and that's what we're going to use so that we can talk to this power supply that we're testing. So I run Linux Mint. You'd have to do PuTTY or something on Windows and find out the exact syntax, but screen works nicely on Linux. And there we go. We can do a help, and it prints out a whole bunch of commands. The one that we're interested in is get source cap for capabilities. And let me scroll up here a little. So Fixed power, 5 volts, 3 amps. We already saw that looked good. 9 volts, 3 amps, 12 volts, 3 amps, 15 volts, 3 amps, 20 volts, 2.25 amps. So ideally you'd go through and test each one of these one at a time, but in the interest of not boring you to death, I'll give you a highlight of what I end up finding here. Now, in order to do this, I'm going to hook the output of this up to these nice big fat resistors. I'm going to jumper them over into into series with my nice big fat rheostat, so I can fine-tune the values of stuff. Now, in order to more easily configure this, let me get this Anker power supply that I was showing you, talking about earlier, out of my way, because this bench is kind of crowded. The reason I've got these white tiles, they're just standard flooring tiles from the hardware store, but they make a nice heat-resistant surface, obviously dissipating power through resistors. When I get up to dissipating 20 volts at a couple of amps, that's a fair amount of wattage that gets put out as heat. You don't want to touch these when you're running, high output, because they get up to several hundred degrees potentially if you're doing a long test. That's why I have these to protect my plastic folding table. So, one of the things that we can, and you see the meter has lit up here, you can't read it, but it's 5.2 volts, 0 amps so far. What we're going to do this test is, you can say output enable. And now it goes to the last profile that I had, which happened to be 20 volts, and it's pushing 1.5 amps. Get this so the cables aren't quite so kinked. It's pushing out 1.5 amps at 20 volts, no problem. Since I happen to be on 20 volts, I'm going to ramp this up a little bit and see if I can get closer to that 2.2. So I hit the max of the dial. I'm on 2.39 amps, going through 8 ohms worth of resistance, and yeah, that's a little bit over the rated amount. The power supply is still putting out 19.9 volts, which in my opinion is pretty close to 20 volts it should be putting out. So that's a very good sign. And then I can do set current space. Let's take a look at the 15 volt profile. 3000 milliamps. Set volts. We wanted 15, so that's 15000. That's just the units it uses. And then write it to the memory. I see this has jumped down to 15.1 volts, so we're down to 1.15 amps on the thing. So what we're going to have to do to test that is reduce the amount of resistance. So I'm going to take one of these out of the circuit and make it just this 4, don't touch this, as I said, this 4 ohm and this 5 ohm. See, we're up to 1.6, so let's crank the dial a little more. 2.1, 2.4, 3.01 and 15.1 volts. I think that's putting out the expected amount of power. So, set volts, and the next profile was 12 volts. Right. 12.1, 1.29. Let's see if we can get this up to 3 amps. Turn the dial, turn the dial. Oop, I hit the end of my dial. I'm at 2.7. We must need to tweak our resistors a little bit more. So, let us modify this circuit a little and put these guys into a parallel circuit so we get 2 ohms through these big fat resistors. This is a little bit tedious because I have to attempt to not touch them. it's not fun. Just take my word for that. Touching a really hot thing isn't fun. So have it go from here through the rheostat back to here. Now, in order to make that a complete circuit, I'm going to jumper from this end of that to this end of this. Now that's got one of those in circuit. Then I'm going to jumper from this end of that, I don't want it touching the aluminum block, to that end of that. Now we should have 2 ohms. So now we have 2 ohms here, 5 ohms there, and I can get as low as 2 ohms if I turn this rheostat all the way up. So we begin cranking on it. 2.23, 2.5, whoop, 3.15, 3.10, 12.0 volts. Oh, wire popped off, dang it. There we go. 12.0 volts, 3.08 amps. I think that's putting out the expected power on its 12 volt profile. So, let's see, I think 9 volts was the next profile. Set V9000. Right. You can keep saying just set V or set I, and then right. It'll go by whatever the last thing is that you set. You can also I think it's get CFG, I believe it is, and it will dump out what the settings are. There's a lot of settings on here. You can set a range of voltages, you can set a wattages, or a whole bunch of different things. What I'm using it for is just telling the power supply, turn yourself on at this volts and amps. That's my interest in it. So any rate, 9.9 volts, 2.3. Let's crank this up, see if we can hit 3. Oops, went a little too far. 3.3 amps. Yeah, it's a little low at 3.3. Let me come down a little bit because I overshot the mark. 3.04 amps, 9.05 volts. So, yeah, at 3 amps, which is what it said it could put out, it's putting out still 9 volts. It's not sagging unreasonably. I think that's also a good test. So, what we're going to do at this point is unplug this, and we will move the meter to the other end of the cable, and I will explain how to test a cable. And plug it in here. I like to have it in CFG mode. You can leave it in normal mode. It'll go by the last setting you wrote, but I like to be able to modify the settings on the fly. That's why I put it, always put it into CFG mode, have it plugged into the computer. It just makes it easier for me personally. There's no other reason really why you'd have to do that. So, let's see if we can get this. It hasn't enumerated itself to the computer yet. There we go. Now it's connected into the computer. You can see it's still got that setting. Oops. It's a space, not a... There we go. Now I've jumped up to 3.07 amps at 8.55 volts. So at the 9 volt profile, 3 amps, we're losing about 0.4 volts. So, do it this way, 6 divided by 9. So, that's within 5% of the voltage that it's supposed to be. Most things will happily take a 5% voltage tolerance if it's over or under by 5%. A lot of things will accept 10% off. I consider that to be reasonable for this 6-foot cable. It's got a lot of cable here bundled up. If you wanted to, you could test it on some other profiles. I can't remember what the 20 amp get. SRC, 20 volt cap. Oops. Okay, what am I doing wrong? Sometimes you just have to go look at the, get source cap, not SRC. .25, so set I 2250 set V 20000 WRITE. Okay, before I write this, I'm going to have a problem because I have this resistance low enough to pull 3 amps at 9 volts. That's going to be a lot more than 3 amps at 20 volts. So before I hit write, got to make sure that this is sufficient resistance, and don't touch the hot bits while you're doing that. So let's rewire this circuit so that it will be safe to switch on the 20 volt profile. Put it back so it goes through everything in series. Now it's down to 0.7 amps. Yeah, I turned that all the way down. And we hit write. 19.6 volts, 1.52 amps. Well, let's see what happens when we crank this sucker up a teeny bit. That's also why I'm using 100 watt rheostat and 100 watt resistors, because they're physically larger, they can dissipate the heat a little bit better. Eventually I hope to put these into a box with a cooling fan, so you don't have to worry about touching them, but for now this works to test stuff. If you had better cooling, you could probably build these into a box with some sort of a liquid cooling type deal. I think people use mineral or not mineral. Is it mineral oil? I forget what it's. There's some people that go into exotic stuff where they have some type of oil that they fill a fish tank with and submerge whole computers in it because it's non-conductive or whatever. You could do something really exotic with that, or like people do with radio dummy loads. Fill up a can of oil and have all the resistors submerged for heat dissipation. Then you could use much physically smaller components and run them at similar ratings, but this is working fine for my needs. I don't do this that frequently. And then when the wires pop off and it breaks the circuit. Alright, so 2.29. 19.6 volts at 2.2, so I think it was 19.9 I said, so 19.6 over 19.9. Oh wow, that's only losing about 1.5% up at the 20 volt profile. That's pretty daggone good for a 6-foot cable in my opinion. So, as I was saying, some cables had that a while ago, and it's just a crap cable. This was a 5-volt cable. This is, power delivery. It can run in more than one voltage, but the same idea applies. You want the power that you're needing to get from one end of the wire to the other without being dissipated as heat and lost somewhere in the wires. That's the end goal, to test a cable to make sure it's going to work good. There's also a lot of people try and plug it into a computer or a phone or something to test. I can show you that here. This is a USBC meter. My computer can run on USB-C. When I plug it into here, see if you can read that. So, yeah, it's pulling 19.6 volts, 1.48 amps, 1.47 amps. The problem with using that as a test to see if your stuff's any good, it depends on the state of what the computer's doing or what the phone's doing, how full the battery is. lots of different variables. That's why the purely resistive load that I use to test is, in my opinion, a better solution. If I do something like reducing the brightness, as it was processing my button presses, it spiked up and then it went way down. You know, if I bring it all the way up, went up a little bit. There's inconsistencies. It doesn't give you a reliable indication of how good the charger or the cable is. That said, this meter's really nifty if you want to know, does my device support what profile? You know, is it charging, is it not charging? This one also shows you the direction of flow, because USB-C power delivery can go both directions. So, you know, you might want to know, is my Nintendo Switch charging my laptop, or is my laptop charging my Nintendo Switch, for example? That sort of a thing. So it's useful as a little gizmo for that. I have a friend that uses one of these other meters, the USB-A one. They put it on their QI charging pad so they can fine-tune the best spot to put the charger pad, that sort of thing. Again, lots of different uses besides just benchmarking the cables and whatnot for these, but you get the idea. It's useful to have on hand. You can use it to measure what your devices do. You can also use it to get a useful idea of you know, benchmarking your power supplies, benchmarking your cables. That's why I'm trying to do this. I want to be able to, independent of the device, identify that the power supply and the cables meet their rated specs. So I hope that's useful for everyone to understand, and I hope that you enjoyed the video. If you have questions or comments, I'd be interested to hear if other people think they have a better system to test this stuff, or think that it's for some reason not representative real-world use. I'm curious to see if someone can improve upon it. I've tried to give it a fair amount of thought, and I haven't been able to come up with anything better yet. I think if you wanted to do this sort of thing for Qualcomm Quick Charge, I believe there was someone working on some sort of a project to use an Arduino or something to command Qualcomm Quick Charge devices to turn on at their higher current rating. I can briefly demonstrate with these meters the quick charge, because I have a phone that supports it. Let me untangle these cables just so you'd see what you'd sort of expect. I can't do a proper, like a benchmark or whatever on it, because I don't have a way to command it arbitrarily and put it on a resistive load, so it's going to be dependent on how much my phone has run down in the last few hours, and how fast the phone is asking to charge, whether or not it wants a higher profile, and a whole laundry list of other things here. It's a LG V30 smartphone in an OtterBox case that I customized a bit. The case does make it slightly harder to plug in. So 1.6, and it seems like this phone prefers USB-C power delivery over Qualcomm Quick Charge, but it eventually does ramp up. I haven't seen it go up to 10 volts before. Usually it seems to want around 8 volts, but you get the idea. You know, it gives you some sort of an idea what it's doing. And you can see it's fluctuating a lot. That's the other reason I don't really like using a phone or something to charge as your indication of how good or bad it is. It's up to the phone or the device what it wants to do. It's not, you know, purely resistive. It's going to be a function of resistance and voltage as to how much current. So it's much more controllable, but this is still useful to gather information about what your things are doing, what they do or don't support. So hopefully that was interesting and appreciated, and I would be interested to see what everyone has to say about this. Thank you for watching.